Hello, everyone. Welcome to the iClub's Physics 72 review for semester 2, 24-25. This is for LE number 1. Today, we will be discussing and reviewing the problem set 1 for this LE. So, for the first question, which of the following charges cannot exist naturally? So, we know that these charges can only exist by the multiples of E. So for example, 54 over 9 is just 6E, which is a whole number. And so the answer, so which of the following charges cannot exist naturally? It's 184 over 13 because if you divide it, it's not a whole number. So charges always have to be a multiple of E. For the second question, three identical conducting spheres denoted as XYZ are separated in space. They have initial net charges of -2, -3, and +5 respectively. Sphere Z is touched to X and separated, then touched to Y and separated. Upon reaching electrostatic equilibrium, what is the final net of charge Y? So for this, it's just a reading comprehension question. Sphere Z is touched to X, so Z touches X, then touched to Y, which means that Z touches Y. So electrostatic equilibrium is just getting the average of the two charges. So at first, uh, -2 touches with +5, which if you average the two will become 3 halves. Then Z touches Y, so 3 halves minus 3, -3 over 2, get the average, equals -3 over 4Q. For the third question, a lot of people got it wrong, but the way it works is that looking at these diagram, we can see that -Q over here and -Q over here can cancel each other out. Because remember that negative particles attract while positive particles push away. So over here, this attracts over here, this attracts over here, this pushes over here, this pushes over here. So we know that -Q here, -Q here, both attract at different directions, but with equal magnitudes. So we can cancel these two out. And so we only have to focus at -Q and +Q over here. And to do the equation, it is the electric field is KQ over R squared. So -KQ over squared of over R squared, squared of 2 over 2A squared. To get the radius, yeah, is because if this entire thing is A, to get to the particle, it's only A over 2. So it's A over 2 only, A over 2, A over 2. And using Pythagorean theorem, it's squared of 2 over 2A. That's why it's squared over 2 over 2A over here. And it's R squared. So the thing with R squared is that it's the vector pointing towards the particle. So this is R squared, but we need I hat and J hat. So R squared is -1 over squared of 2 I hat plus 1 over squared of 2 J hat. To get this exact number, it's the particle here, R hat over this, which is equal to 1. And that means this is I hat, this is J hat, which is 1 over square root of 2, 1 over square root of 2. Using Pythagorean theorem, we can get 1, so 1 over square root of 2, 1 over square root of 2. And we know, since electric field of 1, -Q, this is a negative I hat, positive J hat. And here is a positive I hat, negative J hat, since it's over here, to the right and down, positive, negative, over here. And if we just combine these two together, we'll get square root of 2 over 2, Q naught over pi epsilon naught, negative I hat, positive J hat. But if we don't want to do all of that equations, all we need to do is just look at the directions of the charges. So these two cancel out, we don't need to mind that. This one pushes towards the top left, this one gets pulled towards the top left. So that means it's going up and it's going left. So it is a negative I hats and a positive J hat. For the next question, which of the following charges given the electric field, and the figure is positive. So just remember, positive pushes away, negative pulls in. So R here pushes away, so this is positive. B pulls in, so it's negative. Okay, so this question is similar to the question, this question over here, but it's just a different shape. So something that you should always do is to just draw it out, just so that you can visualize it better. But here, negative Q, positive Q, positive Q, positive Q, negative Q over here. So we can draw the directions of the charges. So this one pulls in, this one pushes away, this one pushes away, this one pulls in, this one pushes away. And a thing you can do is to separate it by the x component, y component, or I hat, j hat. So if we focus on the x component first, we know that the first particle and the last particle don't affect the x component at all, since uh, it's directly at the top and bottom. So electric field 2, it's kq r squared plus 1 over square root of 2 I hat, because it's exactly cosine 45 away, so it's 1 over square root of 2 I hat. This one, negative kq over r squared plus I hat also, it's because it's exactly one, it's exactly to the right of it, that's why it's exactly plus I hat. And this one, same as the bottom, same as particle number 2, kq over r squared, 1 over square root of 2 I hat. And so if we simplify all of this, we can find, and taking the direction into account, we know that it is 1 I hat minus 2 over square root of 2 I hats. So if, again, it's 1 I hat, so it's getting pulled to the right by 1 I hat, and pushed to the left by 2 1 over square root of 2 I hats. 1 over 2 square root of 2 I hats, just in case you didn't know, 2 over square root of 2 can be simplified to 2 times negative 1 half, which is equal to 2 1 half. So it's 1 minus square root of 2 I hat. So 1 minus the square root of I hat. We can stop there, but just for the sake of the reviewer, to get the y component, it's just these two, because this one doesn't affect the y component at all, and these two push each other out. They push each other with the same magnitude. That's why these two cancel each other out for the y component. So for the electric field of number 1, negative kq r squared plus j hat, E2 is kq r squared minus j hat. And just looking at the direction, this pushes towards the top. This gets pulled towards the top. That's why it's 2 j hat over here. So 3 infinite sheets of uniform surface charge densities, positive sigma, and negative sigma, are arranged as shown. What is the magnitude and direction of the net electric field at region 3? So we can draw it again. 1, 2, 3, 4, positive, positive, negative. And we have to remember again that positive pushes away, P for push away, negative pulls in. So at region 1, this pushes, this pulls. Region 2, these two cancel each other out, and there's only one pull. And at region 3, which is what we're looking for, this one pushes down, this one pushes down, this one pulls down. So it's 3 down, so negative 3. That's what you can look for, negative 3. But the actual electric field equation is sigma over 2 epsilon naught. And since there's 3 of them going down, it's negative 3 sigma over 2 epsilon naught j hat. This question is exactly like the previous question, but just with a different orientation. So we're looking for the net electric field in region 4. Region 4 is here. So this one pushes down. This one pulls to the left. So it's negative, negative, negative I hat, negative j hat. For this one, it's a identification question. Which of the following best describes charges x and y? We know both of these are positive because positive repels, P for push, positive push, and negative attracts. So both of them are positive. But something to note is that the more electric field line a particle has, the stronger it is. And so since y has more electric field lines, that means y is greater than x. Okay, this one is a question that a lot of people got wrong, but To explain it, we have to first look at the electric field itself. So the electric field is from bottom to top, and as we know, positive pushes away and negative attracts. So we can imagine it as like a giant plate over here with positive and negative charges. And knowing that, and there's a positive over here, negative over here, and we know that the positive negative attracts with each other. And also, dipoles like these love to take the shortest distance. So from here to get to the negative, the shortest distance is to move 45 degrees clockwise. But something to note also, if the dipole was negative positive like this is an unstable dipole and it could move either way because it's exactly 180 degrees over here. But just remember that look at the electric field lines. Where is it going? P pushes away positive. Take the shortest route. So this question a lot of people got wrong, or a lot of people got careless with this one. But the question is a vase, a shape like a cylinder with its top open, so there's no top, has a radius of r and height h, is placed in a uniform electric field of magnitude E, which at a 45-degree angle from the vertical as shown in figure. What is the electric flux of the base? So the question itself isn't that hard. It's looking for the electric flux, which is EA cos theta. But what's tricky about this is the cos theta, because if you answered cos 45 and got square root of 2 over 2 pi epsilon naught, you would be wrong because the way the theta works is that it is based on the angle from the area. And since the vase has an open top like this, that means the area is facing away from the center of the body. So this is the area. And since the angle comes like this, so, and 45 degrees is this one, it actually is cosine negative 45 because the area is away from the center of the vase. So over here, away from the center of the vase. So that's why it's cosine negative 45 over here. And that's why you get negative square 2 over 2, which gives you negative square of 2 over 2 as your final answer. So for this question, it's a very simple question. Just count how much charge is in each shape. Heart, there's 4 minus 2 is 2. The clubs the clubs is positive 1, and this one's the diamond's equal to 0. Yeah, diamond 0, clubs Q, heart 2Q, and then just make sure to read it properly. Diamond is less than club, less than heart. Okay. This one, a lot of people got careless here as well. So consider a solid sphere inside a spherical conducting shell as shown. The solid sphere has a charge of -4, and the spherical shell has a charge of positive 8. So at first you might look at it and then just do the simple math. 8 plus 4, 8 minus 4, 4. And if you would look at the choices, you would immediately go for this one, like I did as well. But something to note is that K is equal to 1 over 4 pi epsilon naught, which means that 4 over 4 cancels out. So, yeah, it's this one. Q over pi r squared epsilon naught because 4 divided 4. So this one's just a very careless mistake that a lot of people will have. Just remember it's 4 pi epsilon naught. So if it's 4Q over 4, it just simplifies to Q 4 pi epsilon naught. Next one, this one's also another one that a lot of people had careless mistakes on. So a dipole with charges of magnitude 1.5 is placed inside the cavity of a solid conductor. The solid conductor has a net charge of 6. You see what is the total charge of the outer surface of the conductor. So a dipole was like the one we showed, like this one, positive Q, negative Q. So that means they have equal magnitudes actually, because one is positive, one is negative. So even though it says 1.5, it actually just equates to 0. So that's why inside the shell, 0, 0, the solid conductor has a net charge of 6, so 6. So everything outside is just 6. And that's why the answer here is 6. But just in case, just for reviewer's sake, what if it wasn't a dipole inside? What if it was just a normal point charge? Then we should use this equation that the Q in, so example, this is positive 1, let's say positive 1, equals negative Q net of the cavity. So if one was inside, positive 1 was inside, then the Q of the inside of the shell, so over here, is negative of the Q net. So negative 1 is on the outside of the shell. And then Q out is equal to Q net minus Q in. So Q net is 6, while Q in is negative 1. So that means Q out is actually 7, 7. So that's why outside is 7, inside is negative 1, and inside is 1. And the total charge will be 6. So 3-point charges are placed at the 3 corners of a square as shown. What is the total electric potential of the square? We know that electric potential is kq over r, and rr is 3d over square root of 2. Then, so it's just plug and play v1 q, v1 over here, q square root of 2, 3d, that 3 times 4, 12 pi epsilon naught d, q. Add them all together, v1, v2, v3, cancels. So there, square root of 2, q, 12 pi epsilon naught, which is this one. And we can visualize this again. So if you don't want to do the entire equation, joke lang. No, you can't. No, you can't. You can't visualize this since it's only looking for electric potential and not electric force. Electric potential, we have to solve it using VKQ over R. Next, this one is there's a trick to this, but consider a semicircle of radius r with charge q uniformly spread over it, as shown in the figure below. What is the total potential at the center of a semicircle? So the equation to get the potential over something like a semicircle is to get the integral, which is vk r over integral of dq. But we know there's a trick to this. We know that it is charge q uniformly spread over it, which means this entire thing is charge q. And since it's just charge q, the integral of dq is just q. So it's kq over r. So q 4 pi epsilon naught. But something to note is that this equation is true for any shape as long as it's a circular shape and or how big, how small, as long as it's r away and uniformly spread q. So even if there's a particle here and it's like this only, like this semicircle over here, but if this is charge q, this is equal to this because charge q is uniformly spread across it. So if you integrate, even if it's a small thing, if the total charge is q, then it is q, and it's just kq over r. So even if it's a circle, half a circle, part of a circle, as long as it's radius r, it is equal to this equation. So for this question, it's consider cross-section of the equipotential surfaces produced by 2-point charges q1 and q2 as shown. What can be said about the magnitude signs and charges q1, q2? So we know that these are equal to this. So negative 30, 30, they have the same magnitude, negative 20, 20, negative 10, 10. So we know that they have the same magnitude. But we also know that potential travels from higher to lower potentials. So from higher to lower, negative 10 to 30, higher to lower, and this one's higher to lower. So we can see that these two are opposite signs. This one is the negative, this one is the positive. And so, therefore, opposite signs. B. So this one is your differential derivatives, but just make sure to brush up on your derivatives. If you derive e negative dx d sine fx gy, derive it, so it becomes d F, remember to bring out the F, df cos and fx dy d sine fx gy dg cos fx gy. We know it is this one over here. For this question, triple charge, triple threat, consider the ideal parallel plate capacitor with initial charge Q. What happens to capacitance when when the charge and the area of the plates are triple? So over here, we see that capacitance is equal to epsilon naught area over D. So um, charge does not affect the capacitance over here because it's only area, distance, and epsilon naught. Epsilon naught is a constant. So when you triple the area, you triple the capacitance. So you triple 3 times larger. Don't mind this, it's 3 times larger. So what is the potential difference between A and B in the circuit shown? This one was a tricky question, but it's one of the fundamental questions in the circuits. So the potential of a certain capacitor, so VAB, this one, is the charge over the charge in that place over the capacitance of the capacitor. And we know that Q total is equal to the capacitance total times V. And so if we try to find the capacitance, remember capacitors in series, no, if capacitors in series, to add them together, we need to inverse them. 1 over 2 plus 1 over 3 equals to 1 over C. So if we do this, it becomes 5 over 6. And this one becomes 5 over 6 as well. 5 over 6, 5 over 6. And capacitors in parallel, add them together. So the total capacitance is 12 over 5C. So the Q total is just 12 over 5 CV. So charge Coulomb. So we know the Q total is 12 over 5C. And then this is like the shape of our circuit after some simplification, 6 over 5, 6 over 5. But we know, so the way the charge works is that if they're in parallel, then they split the charge. So we have a total charge of 12 over 5, and it gets split into two, 6 over 5, 6 over 5. Since they're the same, it gets split into two. So that means the top part has the same, top part and the bottom part had the same charge, which is both equal to 6 over 5, 6 over 5. And the way charge works in series of capacitors is that capacitors in series share the same charge. So that means 6 over 5 is shared for the 2 over C and 3 over C. So going back to your equation, VAB QBC over 3C, because this is, to get the potential, it is 6 over 5 over 3, which is equal to 2 over 5, which is equal to 2 over 5 over here. So just to note, remember, capacitors in series share the same charge. So 6 over 5 here is 6 over 5 for 2 over C, 6 over 5 for 3 over C. Okay, for the next question, if you increase the charge of a parallel plate capacitor from 3.6 to 36 and decrease the plate separation from 40 to 8, by what factor does the energy stored in capacitor change? So the potential energy is given by this equation. It's capacitance times Q over C squared, Q over capacitance squared over 2. Simplifying it, we get Q squared over 2C. So we also know that C is epsilon not a delta, epsilon not a distance. So we substitute the capacitance here to here. We get potential energy is equal to the distance times the charge squared over 2 epsilon A. So we get this, that the change of potential energy is from 40 to 8, like 40 over 8, times 3.6 to 36 squared. Solving this, we can get that this is just equal to 20 volts. 20, not 20 volts, 20 potential energy, which means it is 20 times bigger than the original capacitor. For this one, It's similar but using a different equation. It is 1/2. The energy density is 1/2 epsilon naught electric field squared. 1/2 epsilon naught is a constant electric field is equal to capacitance times E squared. And then we know that E, if the electric field magnitude is increased by a factor of 6, then we know that if this is 6 inside, 6 squared, 36. U equals 36. Okay, this one, another simple question. It is, what is the new stored energy of the capacitor? So U equals kCV squared, 1/2 kCV squared, K 2.25, so it increases by 2.25. That's it. 2.25 increased by 2.25 is 2.25 more volts compared to the original capacitor, so it's 2.25. Okay, now this one is also something that a lot of people got mistakes on. It's because we know that the equation is J n q v d, and um, if the electron density n is tripled, so when n is tripled, what happens, right? It's obviously it will get 3 times more. But something to note is that Q, it says it is an electron. So that means the Q is negative. Electrons are negative. So that means that the direction of the new current density of the wire is also negative. So that's why it's 3 NeVd downwards. Okay. Something to just remember about ohmic materials is that ohmic materials are linear, and the only linear here is from 10 to 15. So ohmic materials are always linear in their current to voltage graph. Okay, so for this one, it's measuring the resistance of 3 different blocks, and they all have the same internal resistance. So we can just look for the length over the area of all of these things. So here, this is the area, this is the area, this is the length. You just have to plug and play all of them out and find which resistance is the lowest. So R3 is the smallest, number 3 is the smallest. What is the total rate of electricity energy dissipation of the resistor in the given circuit? Power equals V squared over R. V squared over total R in series. Resistors in series, you have to add them together normally. So 4 plus 1 is 5, 5 watts. Okay, this one is just more simplification of resistors. You can draw this entire resistor as this, R1 plus R2 plus R3, R5 plus R4, R6 over here. Combining all of them, you get 3 over 2, 2 over 3, and 5. 2 over 3 and 5. And combining all of these together, you will get this. Um, make sure to remember to inverse this once you're done, because this is just 1 over Req. We have to get Req, which is just this. Okay, this one is a bit similar, but also a bit different. But always the first step whenever you're dealing with circuits is to simplify everything. So over here, we simplify this resistor, and we get equivalent resistance of 2,550. We know that the energy source is 24 volts. So using the V equals IR, we know that the current of the entire circuit is 24 over 2,050. And then to get the current, in of the RC, we just get the current total times the 100 over divide by the times the parallel circuits. And the reason for that is because currents currents in a series, so let's say like this, currents in a series all are equal over here. No matter what, even if there's like 10,000 resistors over here, the current is always the same because there's only one loop. But that's why when it travels here, it's the same current, same current, same current, same current. Oops, it splits into two over here. So the current gets split into two over here. Remember, it's Remember, it's the um, Kirchhoff's loop, not the junction rule. Remember, it's the junction rule. So currents are always the same unless there's a junction over here. And since we know the RB and RC are equal, it gets split into two over here. And that's why when it comes back, it combines back to the original current, which stays all the same. So same current, same current, same current, same current, same current, same current, same current. That's how current works in circuits, in series circuits. And since RB, RC are the same, that's why it got split into two separately. So yeah, 24, 2050, same current, no matter what, but it gets split into two because it splits into two here. Currents stay the same in resistors in series. This one is one of the hardest one or the most complicated one to do. But this is a mix of the junction rule and Kirchhoff's rule. So to give a quick rundown on how junction and Kirchhoff rules work, is that we have our entire circuit and we see a junction here, A. We assign arbitrary current directions. It's arbitrary, so it might be given in the exam, but if it's not given, we just make it arbitrary. So it's I1, I2, I3, and we can just say it all. We can say it all goes into junction A. It doesn't really matter, even if they're all going away or if there's like one going in, two going out. It doesn't matter for this part only, because in the end, in the very end, we'll see like example here, I3 equals negative 4.4A. That means I3 is negative. So our current, like our assumption on the direction of I3 at the start is negative. So that means it actually is pointing downwards. That's how the um, Kirchhoff's rule works. So going back, how do Kirchhoff's rule work? So um, okay, for this one, to get I1, I2, and I3, because we need to find what is the current passing through R3, which is I3, we'll have to use system of equations. So for our first equation, we use the junction rule, which we know I1 plus I2 plus I3 equals 0. This is our first junction rule. First equation, which is the junction rule. And equation and 2 and 3, we use the loop rule to get our equations. So the loop rule, the Kirchhoff's loop rule, is that we will take a loop, any closed loop, and we will just basically count the voltage and the IR, and it should all equate to 0. So for example, here, we use a Kirchhoff's rule going here. We'll take the outer edge. And if we start here, it doesn't matter where you start as long as you do one full loop. We start here, so we go around the circuit, go up here. Just for notation, the longer one is positive. So if you exit through the positive terminal, you will have a positive voltage. So we'll count it. So it goes up here, positive, positive to V. That's our first. Then it goes here. Something to note is that if your loop rule and your assumed current goes to the same direction, it's negative. So that means you are taking negative 2I because V equals IR. We're doing it in terms of voltage everywhere. So it's 2 volts, 2 ohms plus I1. We take the outer circle. Our assumption is I2 is going in. So when we use our loop rule, we are going opposite directions. That means it is plus 1 I2. Go down again. The longer is positive, the shorter is negative. So when we go down here, we exit the negative terminal. That means it is a negative 10 volts. And then we can go all the way around back to start. So that's our equation 2. This is our equation 2. And then for equation 3, we do the same thing, but we use a smaller loop. So for this example, I use this loop. For this loop, it's exactly the same thing. We start here, up positive 2, minus 2I, plus I 3, 1. Because it's opposite direction. Remember, opposite directions take a positive voltage and it goes back. We do the exact same thing to get equation 3, equation 2, equation 1, and then we can use system of equations to find I3. And once you do all of it, it will show I3 equals negative 4.4, which means which means that the entire that means our earlier assumption of what I3 was is wrong, but it's actually going down. It's the opposite way. That's why it's negative, but it's still 4.4 magnitude. That's why it is 4.4 towards junction P. So finally, for our last question, um, what is the voltage of capacitor after two time constants? So time constants is just referring to this. This is what time constants refer to: negative t over tau. Negative t over tau. This is what a time constant is. But it says two time constant, so we can just equate this to two. That's why it's this one, which is equal to 10.4 volts. And just to remember that t equals RC. Oh, tau, I meant, sorry. This is tau. Tau is equal to RC. So that's why initially this is in here. So usually that's why it says initially on charge of 3.5. That's the capacitance there. But it just says two time constants anyways. So this gets cancelled out. But if there was no two time constants, but it said like 5 seconds or something, right? If it said 5 seconds instead, we'll have to use this as our tau to get our time constants and just do this one. It's VC equals V1 minus E time constant, 10.4, 10.4 volts. And that's it. And that's all of the equations of the problem sets. If you have any more questions, you can email or text Uno Angeles for our questions, and he'll answer it all. Thank you.